What's going on, everybody? Mr. Gustin back in the chemistry classroom. Today we're talking about equilibrium, changes in equilibrium, Le Chatelier's principle, and we're kind of following up our discussion on this amazing video that we watched in class yesterday. So what we watched in class was this video with the goldfish. We had a goldfish in one bulb until we opened the reaction. When we opened the reaction, the goldfish were allowed to flow between two bulbs, and eventually they reached a state of equilibrium. We knew that because we could see a constant macroscopic property with our eyes. We saw the same number of goldfish in each bulb, even though they were swimming back and forth. This is equilibrium, all right? Then, later on in the video, we looked to see what happened if I added something to one bulb or the other. This is where the dark fish came into play. We saw the addition of dark fish to one bulb, and as we added to one bulb, they started to swim and equilibrate or return to equilibrium. We saw the same thing with the radioactive bromine. We put radioactive bromine in one bulb, and eventually those radioactive bromines, they transferred over, and we reached this equilibrium. So we came to this statement where it's like, okay, if I have an equilibrium, and then somehow I stress that equilibrium, or I add some chemical to equilibrium, what's going to end up happening is that equilibrium will eventually adjust itself and return to a state of equilibrium. So, this principle, we gave a name. The name we gave this principle was Le Chatelier's principle, okay? We asked a few questions in follow-up. What happened when more fish were added to the bowl? More fish were added to one bowl, so some swam to the other side to reach an equilibrium again. What happened when more radioactive bromine was added? Well, eventually some bromine transferred to the other bulb and returned to an equilibrium. Again, fish and bromine particles were still going back and forth, but they were in a state of equilibrium. So, how does an equilibrium change when more of a chemical is added? It's going to shift to return to the equilibrium. It will shift to the side that was not added to in order to return to that equal state. Let's look at Le Chatelier's principle. So, given the following reaction, A plus B gives me 2C. If I add more A, if I go ahead and say, you know what, I'm going to increase the amount of A here. I'm going to increase the goldfish on this side of the reaction. What's going to happen to C? Well, these little goldfish, these A's, will move this way and cause an increase in the amount of C. This will return it to equilibrium, and eventually we'll be back to where we started at this equilibrium phase. This is what the goldfish say. So another example would be, what if we remove B? So instead of adding things, what if we take something away? Well, this principle holds true, and we want to return to a state of equilibrium. If we decrease the amount of B, something's going to have to happen. We're going to have to move things over here to make up for that loss. What are we going to move? We're going to react some C. So if we remove B, C is going down to cause those goldfish to swim over here and make up for that loss of B. Does this make some sense? I'm hoping this is making some sense, that if we change something in our equilibrium, and here was the change, if we change something, the equilibrium itself will react dynamic molecular behavior in order to cause a change or a shift back. So basically, what we would say here, this is what Mr. Gustin says. I say that when we stress or change an equilibrium, the system basically says, oh yeah, like the Kool-Aid man, and returns itself to equilibrium. So every time we see a shift, we say, oh yeah, how is the equilibrium going to shift to return ourselves back to a state of equilibrium that we were in? Let's look at a few examples, okay? A few examples here. We have three different kinds of changes we're going to look at. The first is a change in concentration. Okay, so here's my equation. I've got A, B, C, and then some energy is produced. So this is an exothermic reaction. We would say that the forward reaction here, this direction is exothermic. We might say that this reaction here is endothermic because energy is required, but we're focused on concentration now. So what happens if we increase the concentration of B? Well, let's treat this equilibrium like the goldfish. I put more chemicals in over here at B. How will the system shift to make up for this? So literally what I'm saying is if I put more of chemical B in this reaction, the reaction is going to drive back to the right. The fish, the chemicals will react moving to the right, which means I'm going to take some B, this is my shift, I can go ahead and star that. B increases, it's going to shift to the right, so in the end, I'm actually going to create more of chemical C. I'm going to create more energy, and in order to do that, B has to react with A. So B brings A along with it, so we actually see a decrease in A. I'll see an increase in B, and then B is going to also decrease to shift and create C and some energy. So the equilibrium will shift away from an increase in concentration, or it will shift towards a decrease in concentration. This is most similar to our goldfish example, all right? So any increase in concentration we shift away from, we say, oh yeah, give me more, I'll shift the other way to balance myself out. Or if we saw a decrease in concentration, we'd say, oh yeah, take away my concentration, I'll create more by shifting towards that decrease. All right? Let's look at temperature. Temperature, we can create. We treat temperature just like any other reactant or product in equilibrium. So where is temperature? Temperature is wrapped up here in energy. So this is really my temperature statement right there. So in this case, if I'm going in this direction, my reaction would be endothermic, because it requires energy to move forward. And my reverse direction would be exothermic, because if F reacts with G, it creates 870 kilojoules. So let's look. What happens if we decrease the temperature of the equilibrium? All right, well, we decrease the temperature of the equilibrium. I'm going to start that because that's my stress. If I decrease the energy, the system's going to say, oh yeah, and shift in that direction to return it to equilibrium. We want this thing to be in the state of equilibrium. If I stress one side, I want to make up for that stress. So I'm going to shift towards that change. I'm going to shift to make up for it. How will it do that? G and F are both going to react together, which is going to decrease the amount of F, decrease the amount of G, and since I'm trying to make energy or release energy, these two chemicals will increase, okay? So our notes basically say an increase in temperature will favor the endothermic reaction. Oh yeah, give me more heat, I'll use it in the endothermic reaction. A decrease in temperature will favor the exothermic reaction. Oh yeah, take away my heat, I'll make more exothermic reaction, okay? And I've defined for you again exo and endothermic. This is the second type of stress that we'll focus on. The last stress we'll focus on are gas stresses, changes in pressure. And changes in pressure are a little different. We haven't necessarily covered gases too much, but we can think back to our goldfish, because the goldfish is a great example, or the bromine gas is a great example of what happens when you change pressure, okay? So right now I've got 4 moles of gaseous H, I've got a mole of gaseous J, 5 moles of gaseous K, and then this is aqueous. This isn't a gas at all, so that's not really going to do anything with pressure. So pressure, when I see pressure, pressure really is dealing with gases. I'm looking at things that are in the gas or vapor states. We're looking here, okay? So what happens if we decrease the pressure? Well, decreasing the pressure here is going to mean there's more room for gas particles. Yeah, we reach a pressure equilibrium like we did with the bromine gas. When I create less pressure, somehow taking pressure away, I'm going to want to fill that space up by creating more gas particles. So a change in pressure talks about more or less room for gas particles. So if I decrease the pressure, I create more space. The system's going to say, oh yeah, give me more space for gas particles, I will use it. I'll fill up that space. Well, which side of this reaction, the forward or the reverse reaction, has more gas particles in it? Well, this side's got 4. This side's got 1 plus 5, 6. This side of my reaction, the forward reaction, is going to create more gas particles to take up that extra space. This is the shift we're going to see. You decrease the pressure, the system will fill the space with more gas particles. On the flip side, if I were to increase the pressure or make less room for particles, it would shift towards the side that has fewer gas particles to alleviate the lack of space that's there. These are the three basic changes that we see, or stresses that we see in our course. There are others, and they get more complex. We'll see a few more complex ones, but these are the basic ones, okay? So now I've got two practice problems for you. I've got this whole chart here. Basically, I've got a change in the reaction, in the equilibrium. I want you to tell me the direction of the shift, and then what happens to this thing right here, okay? And right off the bat, we can go ahead and cross out KEQ. We haven't talked about that yet, so let's cross that sucker out. Not an important thing, okay? So let's go through pretty quickly here. Now, the first change is a decrease in volume. Well, volume is going to be an indicator of gas. I'm going to decrease this volume. I'm going to make less space. So less space when I decrease the volume. If there's less space, this reaction is going to shift towards the side that takes up less space. So if I look up here, which of these takes up less space? This solid takes up really no gas space at all. It's just a solid. I can't change the volume of solid. So I've got 5 particles of gas over here, and I've got 6 particles of gas over here. If there's less space, the reaction says, oh yeah, less space, I will make fewer gas particles. So this side, the left side of the reaction, has fewer gas particles on it, so it shifts left. I'm not concerned about the effect on KEQ, haven't really talked about it. I am concerned with understanding that if I give less space or less volume, the reaction will shift towards the side that takes up less space. Okay? Now, B says, raise the temperature. I'm talking about delta H here. I'm talking about endo/exothermic reactions. And this up here, negative, tells me that the energy is over here. That this is a forward exothermic reaction. So I increase the temperature. Let's do it. I increase the temperature. System says, oh yeah, give me more heat. I will use it. And it uses the heat to drive the reverse reaction. Exothermic, give me more heat, I will use it. Okay, if it's going to use up the heat, what is it going to do to carbon monoxide? Where's carbon monoxide? Carbon monoxide is over here. It's a product of the reverse reaction. So give me more heat, I will use it to balance out my equilibrium, which is going to create more carbon monoxide as a byproduct. C says the addition of I2O5 solid. Now here's the trick. We talked about 3 stresses in this class. The stresses are a change in concentration, a change in temperature, and a change in pressure. Pressure deals with gas particles, temperature deals with energy, and concentration deals with aqueous solutions. Those 3 changes, none of those are associated with the solid state of matter. Solids and liquids will not affect equilibrium states. If I add more solid, it will not impact this equilibrium. If I add more liquid, it will not impact this equilibrium because none of those, solids or liquids, impact temperature, pressure, or concentration. So if I add more I2O5, there is no change. No shift, no change. What if I add CO2? All right, CO2, let's find out where CO2 is. I'm up here, and at the reaction, CO2 is right here. Okay, I increase the amount of CO2. System says, oh yeah, give me more CO2. I'm gonna use it to balance out or return myself to equilibrium. Folks, again, that's going to drive the backward reaction, the reverse reaction. There we go. It's going to force it that way. A byproduct of adding more CO2 is going to be an increase in I2O5. It's one of those products in the reverse reaction. All right, last one. Let's check this out. Last one is the removal of I2. Here's iodine. I'm going to remove I2. There's my shift. System says, oh yeah, take away I2. Take away iodine, we'll make more. How are we going to make more? We got to shift these goldfish, these chemicals, in this direction to make up for the loss. So I need to react carbon monoxide with I2O5 to make up for that. So it's going to shift to the right. What does that do to CO2? Well, CO2 is not a reactant in this reaction, it's actually a product. So these two are going to react to make more I2, and carbon dioxide as a byproduct is going to increase. So this is an example of how we can kind of rifle through just 1, 2, 3, 4, 5 practice problems right on the same exact reaction. Let's try one more together and see if we're getting the hang of this thing. All right, last one. I got this nickel carbon monoxide reaction, okay? Let's go ahead and look and see, are there any solids or liquids in this reaction? If there are, they might not play a role. They will not play a role in terms of the changing reaction. Let's see. So nickel's a solid. Any nickel solid we see, we can say, you know what, no change. There's no change, no shift when you add a solid or a liquid. Right off the bat, they try to trick us with that, and we know, hey, solids are not affecting concentration, temperature, or pressure. So boom, done. I also can look and see that delta H is positive, which means it's an endothermic reaction. So I'm going to put the E here, meaning that this reaction is exo, and that this reaction here is endothermic. So, part B, if I raise the temperature, where does temperature go? Temperature's right here. Oh yeah? Give me more heat. I will use it and drive the reaction forward. Raise the temperature, it's going to shift to the right. What does that do to KEQ? Again, I'm not sure. We haven't studied KEQ yet. That'll come later when we study our math stuff, okay? Raise the temperature, we're going to use it and go with the endothermic reaction because endothermic reactions use energy. All right, what if I add carbon monoxide? System says, oh yeah, give me more carbon monoxide. I'm going to use it and shift to the right. What does that do? Well, carbon monoxide can't create this nickel carbonate, whatever this thing is, without the nickel. So increased carbon monoxide drives the reaction to the right. It's going to consume some nickel on its way to making more product. Part D says, what if I remove nickel, CO4, whatever this stinking thing is? If I take it away, the system goes, oh yeah, take away this stuff, I'll make more to return to equilibrium. So I'm going to shift right to make sure I make up for that. In order to create more nickel, CO4, I need to use these. These two things need to react with each other, consume each other to shift to make more nickel. So what happens to carbon monoxide? Well, that decreases. Ooh, personal favorite. Now we're back to volume. We got a decrease in volume here, okay? If I'm going to decrease the volume, decrease in volume means there's going to be less space for gas particles to hang out. Well, let's count. I've got 4 gas particles over here. I've got 1 gas particle right there. If I create less space, system says, oh yeah, and creates particles or shifts towards the side that takes up less space. Well, folks, tell me, which takes up less space, 4 particles or 1 particle? And the answer is, duh, 1. So we're shifting to the right. We're making only 1 particle. What does that do to the nickel CO4 molecule? Well, we're going to get more of those because they take up less space than the COs, carbon monoxides, alone. F talks about lowering the temperature. Well, that means I'm going to put my energy back there. If I lower the temperature, system's going to say, oh yeah, decrease my heat. I will make more heat by favoring the exothermic reaction. It's going to shift this way to make up that heat. While I make that heat or release that energy, a byproduct is nickel. Another byproduct would be carbon monoxide. So the carbon monoxide volume or amount increases. Last one's a KEQ. I'm not sure what KEQ is yet, but we'll get back to that. I still want to talk about the shift. If I remove carbon monoxide, I take this stuff away, system goes, oh yeah, take some of this away. I'll make more of it by shifting to the left to fill that space. Shifts left to make more carbon monoxide once you take it away. Okay, right now this is theoretical stuff. We're just talking about basically, can we read an equilibrium expression, and can we talk about the shifts that'll happen as we get through later into the week. We're going to design an experiment, or not an experiment, we're going to design some reactions and some procedures to help us actually control equilibrium reactions and see how changing concentrations changes the favorability or the side of a reaction that is favored. Okay, so your homework right now, the time left in class, go through, finish the rest of the practice on this, and I'll check in with you when I get back tomorrow. All right, see ya.